Welcome to Still Science Lab. Tonight, we are staring directly into the containment field of the most dangerous, expensive, and potentially revolutionary substance in the known universe. We are looking at the recent, record-breaking achievements of the Alpha experiment at CERN, a milestone that forces us to ask a question that has haunted physics for a century. Have we finally found the key to infinite energy? Or have we simply built the ultimate self-destruct button for mankind? The title of our investigation tonight is CERN Found the Key to Infinite Energy, the Alpha Experiment Record. And what we are about to discuss is not science fiction. It is happening right now, beneath the border of France and Switzerland, where scientists have just managed to trap the ghost of the universe. For the better part of 2 decades, the concept of antimatter has existed in the public consciousness largely as a plot device, a terrifying MacGuffin popularized by Dan Brown's novel Angels and Demons. In that story, a quarter gram of antimatter is stolen from CERN, suspended in a portable magnetic trap, a glowing canister that ticks down like a time bomb. The threat in the narrative is visceral because the physics behind it is theoretically sound. If that magnetic battery were to fail, if the antimatter inside were to touch the physical walls of the canister, the result would be a cataclysmic explosion over the Vatican. The horror of that image lies in the efficiency of the reaction. When matter meets antimatter, they do not just burn, they annihilate. They convert 100% of their mass into pure, unadulterated energy, following Einstein's famous equation, E equals mc squared. To put that in perspective, a nuclear weapon, the most destructive force we have ever engineered, converts only a tiny fraction of 1% of its mass into energy. Antimatter is the only fuel in the universe that is 100% efficient. It is the holy grail of propulsion and the ultimate nightmare of warfare. For years, physicists have watched movies like Angels and Demons or Star Trek and smiled politely, dismissing the idea of an antimatter battery as pure fantasy. They would explain that while the math is correct, the engineering is impossible. They would tell you that antimatter is too volatile, too rare, and too hot to ever be captured in significant quantities. They would say that we can create it, particle by particle, but we can't hold it. It is like trying to catch a lightning bolt in a glass jar. The moment you close the lid, the jar shatters. But as we move through late 2025, and into the early months of 2026, those polite smiles are beginning to fade, replaced by a look of intense, focused seriousness. The narrative has shifted. The impossible engineering is no longer impossible. The news coming out of the Alpha collaboration at CERN has sent a shockwave through the scientific community. The headlines are not about the discovery of a new particle, but about the domination of an old one. The researchers have announced a breakthrough in the laser cooling of antihydrogen atoms, achieving cooling rates 8 times faster than anything previously recorded. This number, 8 times faster, might sound like a dry statistic, a mere incremental improvement in a spreadsheet. But in the world of quantum mechanics, it is the difference between catching a blur and holding a statue. It is a leap in capability that transforms antimatter from a fleeting curiosity into a tangible, studyable sample. We are no longer talking about detecting a few stray atoms that vanish in a microsecond. We are talking about trapping, holding, and actively manipulating a cloud of 15,000 anti-atoms. To understand the magnitude of this shift, we have to appreciate the sheer hostility of the material we are dealing with. Antimatter is the mirror image of everything we know. It is the evil twin of normal matter. For every proton in your body, there is a theoretical antiproton with the same mass but a negative charge. For every electron, a positron. If you were to shake hands with your antimatter twin, the energy released would be equivalent to thousands of megatons of TNT. Because we live in a universe made of matter, antimatter is effectively born behind enemy lines. The moment it comes into existence, it is surrounded by things that want to destroy it. Air molecules, the walls of the vacuum chamber, even the thermal radiation of the room itself. Everything is a lethal threat to an antimatter atom. Keeping it alive is the hardest magic trick in physics. Before this recent breakthrough, trapping antimatter was like trying to balance a needle on its tip during an earthquake. The anti-atoms created in the particle accelerators are born hot. They are moving with ferocious speed and energy. To keep them in a magnetic trap, you have to slow them down. You have to cool them to temperatures within a whisper of absolute zero. If they are too hot, they simply punch through the magnetic field and annihilate against the container walls. For decades, this cooling process was slow, inefficient, and agonizingly difficult. We could catch a few atoms, perhaps a dozen, and hold them for a breath before they escaped or were destroyed. It was a scientific parlor trick, proof that it could be done, but useless for any practical application. The breakthrough of 2026 changes the geometry of the problem. By utilizing a new, advanced form of laser cooling, essentially bombarding the anti-atoms with photons that are perfectly tuned to slow them down. The Alpha team has managed to freeze these particles in their tracks almost instantly. They have created a thermal halt. This allows them to stack the atoms, to accumulate them, building up a reservoir of antimatter that was previously unthinkable. 15,000 atoms may still sound like a small number compared to the trillions of atoms in a grain of sand, but in the context of antimatter research, it is a massive stockpile. It is enough to form a cloud. It is enough to perform gravity tests. It is enough to shine a light on and see what color the mirror universe truly is. This transition from hunting to farming antimatter brings the sci-fi dream uncomfortably close to reality. We are witnessing the first steps toward the containment technology seen in fiction. The magnetic bottle is no longer just a concept, it is a prototype. Of course, we are not yet at the stage where we can power a starship or level a city. The energy required to create these 15,000 atoms still far exceeds the energy they would release if they annihilated. The cost is still astronomical. Estimates place the value of a single gram of antimatter at over $62 trillion. But technology has a habit of moving slowly, and then all at once. The first computer filled a room. The one in your pocket is 1,000,000 times more powerful. We are at the ENIAC stage of antimatter technology. We have built the room-sized machine that does the basic calculation. The question now is not if we can store it, but how much and how long. This reality check forces us to confront the dual nature of this discovery. On one hand, the mastery of antimatter offers the promise of the ultimate energy source, a fuel so dense that a few milligrams could take a spacecraft to Mars in weeks instead of months. A source of power that produces no nuclear waste, no greenhouse gases, just pure, radiant energy. It is the dream of a Type 1 civilization. On the other hand, it opens the door to the ultimate weapon. If we can trap 15,000 atoms today, What happens when we can trap a mole? What happens when the containment becomes portable? The alpha experiment has shown us that the barrier to storing antimatter is not a fundamental law of physics, but merely an engineering challenge. And engineering challenges are eventually solved. So, as we stand here tonight, looking at the data from Geneva, we are looking at a threshold. The universe has kept this substance hidden from us for 13.8 billion years, creating a cosmos where matter dominates and antimatter is a ghost. By reaching into the void and pulling these ghosts into the light, by freezing them and holding them in a magnetic cage, we are defying the natural order. We are rewriting the script of the cosmos. The 2026 record at CERN is not just a victory for high-energy physics. It is a signal that humanity is ready to touch the third rail of reality. We are no longer just observing the fireworks of the universe. We are learning how to manufacture the gunpowder. The era of the angels and demons fantasy is ending, and the era of the antimatter reality has begun. To understand the sheer magnitude of what CERN is grappling with, we must first strip away the science fiction tropes and look at the fundamental architecture of our reality. When we look in a mirror, we see a reflection of ourselves. It looks like us, moves like us, and mimics our every gesture, but we know intuitively that it is not real. It is just light bouncing off a silvered surface. But in the deep mathematics of the universe, there is a reflection that is terrifyingly real. It is not made of light, but of substance. It has mass, it occupies space, and it obeys the laws of physics just as we do. This is the realm of antimatter. It is the physical embodiment of the universe's obsession with symmetry, a mirror universe that exists as a perfect inverted copy of our own. At its core, matter, the stuff that makes up your body, the air you breathe, and the screen you are reading this on, is built from atoms. These atoms are constructed from subatomic particles with specific electrical charges. The proton, residing in the nucleus, carries a positive charge. The electron, orbiting the nucleus like a frenetic satellite, carries a negative charge. This electrical balance is the glue of existence. It allows atoms to bond, molecules to form, and life to emerge. But in 1928, the physicist Paul Dirac stared at an equation that described the behavior of electrons and realized something profound. The math didn't just work for the negative electron, it also worked perfectly for a particle that had the exact same mass but a positive charge. It was a mathematical ghost, a prediction that for every particle of matter there must exist an antiparticle. This is the definition of antimatter. It is not some exotic, magical substance made of different ingredients. It is made of the same fundamental stuff as us, simply flipped. An antiproton is a proton with a negative charge. A positron is an electron with a positive charge. If you could somehow gather enough of these antiparticles together, you could build anti-atoms. You could combine an antiproton and a positron to create antihydrogen, which is exactly what the alpha experiment at CERN has done. If you had enough antihydrogen, you could theoretically build anti-water. You could build anti-stars, anti-planets, and even anti-people. This brings us to the most unsettling analogy in physics, the concept of the evil twin or the doppelganger. Imagine you are walking down the street and you see someone walking toward you. As they get closer, you realize they look exactly like you. They have the same height, the same hair color, the same scars, and the same memories. To an observer watching from a distance, the two of you are indistinguishable. You are identical in every physical measurement except one. Your electrical charge is reversed. This sounds like a harmless difference, a minor technicality in the wiring of the universe, but it dictates the single most violent rule in nature. In the folklore of doppelgangers, seeing your double is an omen of death. In the physics of antimatter, touching your double is a guarantee of annihilation. The interaction between matter and antimatter is unlike any other collision in the universe. When two normal cars crash into each other, metal crunches, heat is generated, and debris flies everywhere, but the mass of the cars remains. The atoms are rearranged, but they are not destroyed. Even in a nuclear explosion, like the fission bombs that leveled cities in the 20th century, we are only converting a tiny fraction of the mass of the uranium or plutonium into energy. The vast majority of the bomb's material remains as radioactive fallout. Nuclear fusion, the process that powers the sun, is more efficient. But even then, it only converts about 0.7% of the mass into energy. These are violent reactions, yes, but they are messy and incomplete. Antimatter annihilation is different. It is clean, absolute, and total. Because the particle and the antiparticle are perfect opposites, when they meet, they cancel each other out completely. It is like adding +1 and -1. The result is 0, but in physics you cannot just have 0. The mass cannot simply vanish. Instead, according to Einstein's famous equation, that mass is converted entirely into energy. The particle and the antiparticle cease to exist as matter. They disappear from the physical universe, and in their place, a burst of pure energy is born. This usually takes the form of high-energy gamma rays, the most piercing and powerful form of radiation. This is why the reaction is so terrifyingly efficient. It is 100% conversion. Every single proton and antiproton involved in the collision is transformed into light and heat. There is no leftover debris, no ash, no scrap metal, just a flash of blinding intensity. This efficiency explains why a microscopic amount of antimatter is equal to a mountain of chemical fuel. To visualize this, consider a simple paperclip. A standard paperclip weighs about 1 gram. If you were to construct a paperclip out of pure antimatter, an anti-paperclip, and carefully touch it to a normal paperclip, the resulting explosion would be catastrophic. The annihilation of just 1 gram of antimatter with 1 gram of matter would release energy equivalent to roughly 43 kilotons of TNT. That is about 3 times the power of the atomic bomb dropped on Hiroshima. 2 paperclips vanishing in a nanosecond could level a modern metropolis. This extreme energy density is why antimatter is the ultimate double-edged sword. It represents the potential for infinite clean energy, a fuel source so potent that a few milligrams could power a city for weeks. But it also represents the ultimate destructive capacity. The mirror universe is therefore not a parallel dimension or a different timeline. It is a potential state of our own reality. The fact that we can create these particles, even for a fleeting fraction of a second, proves that the mirror is real. In fact, we see this mirror in action in mundane ways. Hospitals use positron emission tomography, or PET scans, to image the human body. The P in PET stands for positron, the antimatter partner of the electron. When a patient gets a PET scan, they are injected with a tracer that emits tiny amounts of antimatter inside their body. These positrons travel a fraction of a millimeter before hitting an electron in the patient's tissue. They annihilate, sending out a pair of gamma rays that the scanner detects. We are effectively using tiny, controlled antimatter explosions to diagnose cancer. However, the challenge that has plagued scientists since Dirac's discovery is that the mirror is incredibly fragile. In a universe dominated by matter, an antimatter particle is a stranger in a strange land. It is born surrounded by its enemies. An antiproton created in a particle accelerator has to navigate a vacuum tube, because if it hits a single air molecule, a single nitrogen or oxygen atom, it will annihilate instantly. This is why the mirror universe usually only exists for microseconds. The particles are born, they travel a few inches, they hit something, and they die in a flash of light. They are ephemeral ghosts, flickering in and out of existence before we can even study them. This inherent volatility creates a profound tension in the study of physics. We know that the laws of nature treat matter and antimatter almost exactly the same. Gravity should pull on an anti-apple just as it pulls on a real apple. Light should bounce off an anti-mirror just as it bounces off a real mirror. An anti-star should shine just as brightly as our sun. If you were to look at a galaxy made entirely of antimatter, you wouldn't be able to tell the difference through a telescope. It would look identical. The only way you would know is if you tried to land a spaceship on one of its planets. The moment your landing gear touched the surface, the ship and the landing pad would vanish in a burst of gamma radiation. The existence of this mirror capability suggests that the universe has a deep, underlying symmetry. It implies that for every piece of the puzzle we hold in our hands, there is a corresponding piece that fits it perfectly but destroys it upon contact. It forces us to view our reality not as the only possible reality, but as one half of a duality. We are the positive side of the equation, living in a world that has somehow forgotten its negative counterpart. The Alpha experiment is essentially trying to reconstruct that lost half, brick by brick, atom by atom. By trapping antihydrogen, we are holding a piece of the mirror still enough to see our own reflection. Understanding this definition, opposite charge, same mass, total annihilation, is crucial because it sets the stakes for everything that follows. When we talk about trapping 15,000 atoms, we are not trapping sand in a bucket. We are trapping 15,000 tiny potential explosions. We are trapping a substance that fights for its life against the very container that holds it. We are holding a drop of the mirror universe in the palm of our magnetic hand, fully aware that if we flinch, if the trap fails, the mirror breaks. And in the world of antimatter, a broken mirror doesn't bring 7 years of bad luck. It brings a release of energy that creates a miniature sun on Earth. This is the substance CERN has tamed. It is the perfect opposite, the ultimate fuel, and the silent twin that has been waiting in the dark since the beginning of time. To exist is to defy the odds. When you look at your hand, or the chair you are sitting on, or the stars scattered across the night sky, you are witnessing a monumental statistical error. According to the strictest interpretations of the laws of physics that govern the birth of our universe, none of this should be here. The universe should be a vast, cold, and empty expanse, devoid of stars, planets, and life. It should be filled with nothing but the dim hum of leftover radiation. The fact that we are here to ask questions about our origins is the single greatest paradox in cosmology. We call this the baryon asymmetry, or the matter-antimatter asymmetry, but a more visceral name might be the Great Cosmic Mystery. We are the survivors of a war that ended before it truly began, and the experiments at CERN are not just looking for particles. They are hunting for the reason we were allowed to survive. The paradox begins with the nature of creation itself. In the initial fireball of the Big Bang, some 13.8 billion years ago, the universe was infinitely hot and infinitely dense. In this primordial furnace, energy was constantly converting into mass, and mass was turning back into energy. This is Einstein's famous equation in action. Energy equals mass times the speed of light squared. However, nature enforces a strict balance sheet. You cannot simply create matter out of nothing without a cost. For every particle of matter created every negative electron and positive proton, the universe must create an equal and opposite twin, an antiparticle. For the electron, there is the positron. For the proton, the antiproton. This is not a suggestion. It is a fundamental conservation law. Energy must be conserved, and charge must be conserved. To make a plus, you must make a minus. If the Big Bang was a perfect process, it should have produced exactly 50% matter and 50% antimatter. The universe should have been a perfect mirror with equal armies of particles and antiparticles emerging from the energy soup. As the universe expanded and cooled, these opposing armies would have collided. And as we discussed, when matter meets antimatter, they annihilate. They destroy each other instantly, releasing their mass back as energy. In a perfectly symmetrical universe, this great annihilation would have been total. Every proton would have found an antiproton. Every electron would have found a positron. They would have cancelled each other out completely, leaving behind a universe made of pure light, a cosmic flashbulb going off, followed by eternal darkness. There would be no leftover atoms to form gas, no gas to form stars, and certainly no carbon to form human beings. The equation should have summed to zero. Yet, we are here. When we look out into the cosmos with our telescopes, we see galaxies made of matter. We see gas clouds made of matter. We do not see vast regions of antimatter. If there were antimatter galaxies out there, the boundary between them and our matter galaxies would be a blazing wall of gamma radiation from the constant annihilation of intergalactic gas. But the sky is quiet. The gamma ray detectors on our satellites see a diffuse glow, but nothing that indicates a massive war between matter and antimatter sectors of the universe. This means that, somehow, in those first fractions of a second, the balance was broken. The great annihilation did happen, but it wasn't perfect. Physicists estimate that for every billion particles of antimatter created in the Big Bang, the universe created 1,000,000,001 particles of matter. It was a tiny, almost imperceptible imbalance, a fluctuation of 1 part in a billion. When the universe cooled and the annihilation began, the billion pairs destroyed each other, filling the cosmos with the background radiation we can still detect today. But that one extra particle, the survivor, had no partner to kill it. It remained. It floated alone in the cooling void. Over time, those lonely survivors clumped together. They formed hydrogen, then helium. Gravity pulled them into stars, which forged heavier elements. Eventually, those elements formed planets, and on at least one planet, they formed us. All the stars, all the galaxies, and every atom in your body are made from those leftover 1 in a billion survivors. We are the cosmic rounding error. The standard model of particle physics, for all its success, cannot fully explain this. It allows for a tiny amount of asymmetry, known as CP violation, but nowhere near enough to account for the sheer amount of matter we see. If we rely solely on the equations we currently have, the universe should still be empty. There must be a mechanism, a rule breaker, that intervened in the early universe to favor matter over antimatter. This is the cold case that CERN is trying to solve. The universe committed a crime. It stole the antimatter and left the matter, and we are trying to find the fingerprint of the culprit. This brings the significance of the alpha experiment into sharp focus. We are not trapping antihydrogen just to prove we can. We are trapping it to interrogate it. If matter and antimatter are truly perfect reflections of each other, then the Big Bang makes no sense. Therefore, there must be a flaw in the reflection. There must be some tiny, subtle difference between a hydrogen atom and an antihydrogen atom that allowed matter to win the war. Perhaps the antihydrogen atom has a slightly different mass. Perhaps its magnetic moment is slightly off. Perhaps it interacts with gravity in a way that is just a fraction of a percent different from normal matter. By trapping 15,000 atoms of antihydrogen and holding them still, the scientists at CERN are effectively building a time machine. They are recreating the conditions of the early universe in a bottle. They are freezing the suspect to take its mugshot. They shine lasers on these trapped anti-atoms to measure their spectrum, the specific colors of light they absorb and emit. If the spectrum of antihydrogen is identical to hydrogen, the mystery deepens. But if the laser frequency is different, even by a tiny fraction of a decimal point, it would be the smoking gun. It would prove that the laws of physics are not symmetrical. It would reveal the crack in the mirror that allowed us to exist. This mystery also forces us to confront the terrifying possibility of where the antimatter went. Some theories suggest it didn't disappear, but was separated. Perhaps the universe is much larger than the observable bubble we see, and beyond our horizon, there are vast oceans of antimatter, forever out of reach. In that scenario, we are living in a matter pocket of a much grander, segregated cosmos. Other theories suggest that the antimatter was processed into something else entirely, perhaps dark matter, hiding in the halos of galaxies, invisible but heavy. Or perhaps, and most unsettlingly, it simply vanished because the fundamental constants of nature were different when the universe was hot. The gravity of this question cannot be overstated. We often take our existence for granted. We wake up, go to work, and live our lives assuming that being is the default state of the universe. But the study of antimatter tells us that non-being is the default. The natural state of the universe is equilibrium, and equilibrium means death. The fact that we are here means that the universe is fundamentally out of balance. It is tilted. The alpha experiment is trying to measure the angle of that tilt. When the researchers at CERN look at their monitors and see the data form those 15,000 trapped atoms, they are looking for a discrepancy. They are hoping to find that nature is imperfect. In most sciences, you look for symmetry and order. In antimatter physics, we are desperate to find chaos and disorder. We want to find the rule that was broken. Because if we find that matter and antimatter are truly identical in every way, then our current understanding of the Big Bang is fundamentally wrong. It would mean that some other force, something outside the standard model, something we haven't even imagined yet, reached into the cauldron of creation and saved us from annihilation. So, as we stare into the vacuum trap at CERN, we are staring into the abyss of our own history. We are looking for the missing siblings of the protons in our bodies. They are gone, annihilated billions of years ago, their energy scattered across the sky as the cosmic microwave background. We are the leftovers, the residue, the ash that refused to burn. And the hunt for the properties of these trapped anti-atoms is the hunt for the reason why the fire stopped. It is the ultimate existential detective story, written in the language of laser spectroscopy and magnetic confinement. We are not just studying a rare particle, we are asking the universe why it decided to let us live. And the answer, if it exists, is locked inside that magnetic field, waiting for us to decipher the code. To comprehend the engineering miracle that has taken place at CERN, one must first appreciate the sheer physical paradox of the task at hand. In the history of science, the container has always been as important as the content. If you discover a new acid, you store it in glass. If you harvest a dangerous gas, you compress it in steel. If you isolate a radioactive isotope, you shield it in lead. But antimatter defies every conventional rule of storage. It presents a problem that sounds like a riddle from a fantasy novel. How do you hold a substance that destroys anything it touches? There is no material in the known universe, no diamond, no titanium, no force-hardened alloy that can hold antimatter. To an atom of antihydrogen, a wall of solid steel is not a barrier, it is a minefield. The moment the anti-atom grazes the surface of the container, it encounters the protons and electrons of the metal. The result is instant, violent annihilation. The container does not just fail to hold the contents, the container ceases to exist at the point of contact, and the contents vanish in a burst of gamma radiation. This is the universal solvent problem. In alchemy, the universal solvent was a mythical substance that could dissolve anything. The alchemists never stopped to ask what they would keep it in, for it would dissolve the bottle. Antimatter is the real-world equivalent of this myth. Therefore, the bottle cannot be made of matter. It must be made of something else. It must be made of intangible forces. It must be a cage constructed not of bars, but of pure energy. This brings us to the first layer of the engineering challenge, the vacuum. Before we can even think about trapping the particle, we must clear the stage. The air you are breathing right now is a thick, chaotic soup of nitrogen, oxygen, and argon atoms. To an antimatter particle, the air in this room is as dense and deadly as a wall of lead. If you were to release an antiproton here, it wouldn't travel more than a few centimeters before hitting an air molecule and exploding. To give antimatter a chance to survive, engineers must create a void that rivals the emptiness of deep space. The experimental chambers at the Alpha experiment are pumped down to an ultra-high vacuum. We are talking about pressures so low that they are measured in trillionths of an atmosphere. In this environment, a stray gas molecule is a rare event. This extreme emptiness is the canvas upon which the trap is painted, ensuring that the only thing the antimatter has to worry about is the wall of the chamber itself. With the air removed, we face the second, more insidious challenge: gravity and thermal motion. Even in a perfect vacuum, an atom will fall due to gravity, or it will bounce around due to its own heat energy. If it falls or bounces, it hits the wall. Game over. To stop this, scientists employ the penning trap, a device that acts as the initial holding cell for the raw ingredients of antihydrogen. A penning trap is a brilliant application of electromagnetism. It uses a combination of static electric fields and a strong magnetic field to confine charged particles. Imagine a bowl. If you put a marble in a bowl, gravity pulls it to the bottom, and the sides keep it from rolling out. A penning trap creates an electromagnetic bowl for charged particles. The physics relies on the Lorentz force. When a charged particle, like an antiproton or a positron, moves through a magnetic field, it is forced to travel in a circle. It spirals around the magnetic field lines, unable to cross them. It is like a bead on a string. The electric field then caps the ends of the string, bouncing the particle back and forth. Inside this trap, the ingredients of antimatter can be held suspended in the center of the vacuum tube, levitating in a magnetic cradle, never touching the physical walls. This technology is mature. We have been trapping ions this way for decades. However, the alpha experiment is not just trying to trap ingredients, it is trying to trap the final product, antihydrogen. And here is where the engineering difficulty spikes vertically. Antihydrogen is made by mixing an antiproton, negative, and a positron. When they combine, the charges cancel out. The resulting atom is electrically neutral. Suddenly, the Penning trap stops working. The electric fields have nothing to grab onto. The magnetic field lines can no longer force the particle to spiral. The bead falls off the string. The newly formed antihydrogen atom is invisible to the electric cage. It is free to fly in a straight line, right into the walls of the chamber. To catch a neutral ghost, the engineers have to exploit a much subtler property of the atom, its magnetic moment. Although the atom has no net electrical charge, it acts like a tiny subatomic bar magnet. It has a north and a south pole due to the spin of its internal particles. This means it can still interact with a magnetic field, but only if the field is shaped in a very specific, complex way. This is known as a minimum B trap or an Ioffe-Pritchard trap. Imagine the magnetic field not as a set of lines, but as a landscape. The engineers use massive, superconducting octopole magnets to create a magnetic bathtub in the center of the vacuum chamber. In this landscape, the magnetic field is weakest in the absolute center and gets stronger as you move toward the walls. For an antihydrogen atom with the right spin, moving toward the strong magnetic field at the wall is like trying to roll a ball up a steep hill. The magnetic force pushes it back toward the center, toward the bottom of the bathtub. But this magnetic hill is incredibly shallow. The force is weak, laughably weak compared to the electric forces used in the Penning trap. This brings us to the struggle that has defined the last 20 years of research: temperature. In the world of atoms, temperature is just a measure of speed. A hot atom is moving fast. A cold atom is moving slow. When antihydrogen is formed by smashing antiprotons and positrons together, the resulting atoms are often born hot. They are moving with significant kinetic energy. The magnetic bathtub created by the alpha trap is very shallow. If the antihydrogen atoms are moving too fast, even if too fast is just the speed of a gentle walking pace, they will have enough energy to roll right up the magnetic hill and smash into the wall. It is like trying to keep a handful of hyperactive fleas inside a shallow saucer. If they jump, they are gone. For years, this was the tragedy of the experiment. Scientists would create thousands of antihydrogen atoms, but they were all too hot. They would simply fly over the magnetic barrier and annihilate instantly. The detectors would register the explosion, confirming the atoms existed, but they couldn't be held. They were dead on arrival. The engineering challenge, therefore, became a war against heat. To trap the antimatter, the entire apparatus had to be cooled to temperatures colder than deep space. The magnets themselves are superconducting coils cooled by liquid helium to 4 degrees above absolute zero. The interior of the chamber is chilled to create a cryogenic environment where thermal radiation is minimized. Every fraction of a degree matters. If the walls are too warm, they emit photons that can strike the antimatter and give it just enough energy to escape the trap. Historically, this has been a game of agonizing attrition. In the early days, around 2010, the success rate was pitiful. They would mix millions of antiprotons and positrons, creating thousands of antihydrogen atoms, and out of that chaotic swarm, maybe one, just one, would happen to be moving slowly enough to get caught in the shallow magnetic bathtub. The scientists would hold their breath, watching the monitors, hoping that the single atom would stay stable. For a long time, success was measured in milliseconds. They would trap an atom for 1/10 of a second before it escaped, or a stray gas molecule killed it. It was a fleeting victory. You cannot study something that disappears in the blink of an eye. You cannot measure its spectrum. You cannot test its gravity. You can only say, it was here. This struggle is what makes the bottle analogy so poignant. We are not building a bottle out of glass. We are building a bottle out of probability and magnetic gradients. We are trying to construct a force field that is strong enough to push back against the momentum of the atom, but precise enough not to distort the measurements we want to take. The walls of this bottle are invisible, but they are the most expensive walls in history. They require miles of superconducting wire, endless liters of liquid helium, and a control system that can adjust the magnetic fields with microsecond precision. The engineering challenge is effectively a battle against the disorder of the universe. Thermodynamics wants the atoms to be hot. Entropy wants the vacuum to be filled. Gravity wants the atoms to fall. The engineers at CERN are fighting all three of these fundamental forces simultaneously. They are trying to carve out a tiny, calm island in a chaotic universe, a sanctuary where the laws of annihilation are temporarily suspended. The fact that they could trap even one atom was a triumph of human intellect, but one atom is not a fuel source. One atom is not a weapon. One atom is a curiosity. To move from curiosity to capability, they needed to deepen the bathtub. They needed to stop the fleas from jumping. They needed to find a way to take the energy out of the system faster than it could be put in. This need for speed, the need to cool the atoms down before they could escape, set the stage for the breakthrough that would finally allow them to screw the lid onto the bottle. The struggle to contain the most volatile substance in existence has always been a race against time and temperature. But as we enter 2026, the rules of that race have been fundamentally rewritten. For years, the Alpha experiment at CERN was limited by a frustrating bottleneck: the sheer speed of the anti-atoms they created. No matter how perfect the vacuum or how strong the magnetic fields, the antihydrogen atoms were born with too much kinetic energy. They were simply too hot to be effectively managed. But the recent news from the CERN laboratories marks what many are calling a quantum leap in antimatter manipulation. The breakthrough involves a revolutionary advancement in laser cooling technology that has allowed scientists to chill antihydrogen atoms at a rate 8 times faster than anything previously achieved in human history. This is not just a minor improvement. It is a game changer that transforms antimatter research from a game of lucky catches into a systematic industrial process. To understand why cooling 8 times faster is so significant, we have to look at the delicate physics of a laser beam. In our everyday experience, we think of lasers as sources of heat tools used to cut through steel or perform surgery. But in the strange world of atomic physics, a laser can act as a fire extinguisher. When a photon from a laser strikes an atom moving toward it, the atom absorbs the photon and receives a tiny kick in the opposite direction. If you tune the frequency of the laser just right, a process known as Doppler cooling, you can ensure that the atom only absorbs photons that are moving against its motion. It is like trying to slow down a speeding car by pelting it with millions of ping-pong balls. Each individual impact is negligible, but collectively, they drain the car's momentum until it comes to a crawl. In the 2026 Alpha update, the engineering team successfully implemented a new, high-repetition rate ultraviolet laser system specifically designed to interact with the unique energy transitions of antihydrogen. Historically, cooling antimatter was a slow and agonizingly inefficient process. Because the magnetic bathtub used to hold the atoms is so shallow, many atoms would simply fly out of the trap before the lasers had enough time to slow them down. You were essentially trying to catch a swarm of bees with a net made of light while the bees were moving at supersonic speeds. Most of them escaped before you could even bring the net to bear. By increasing the cooling speed by a factor of 8, CERN has effectively closed the exit door. The lasers now grab the antiatoms almost the instant they are formed, draining their heat and settling them into the center of the trap before they have a chance to touch the walls and annihilate. This leap in speed has profound consequences for the stability of the experiment. When you cool an atom 8 times faster, you aren't just saving time, you are increasing the density of the sample. In previous years, the Alpha experiment could only hope to hold a handful of atoms at a time because the hot atoms would constantly collide with and knock out the cold ones. It was a one-in, one-out scenario that kept the total count extremely low. With the 2026 breakthrough, the cooling is so rapid that the anti-atoms become frozen in place before they can interfere with one another. This has allowed the team to begin stacking pulses of antimatter, accumulating a population that is orders of magnitude larger than anything we have seen before. This is the moment where we move from trapping a single curiosity to maintaining a stable, controllable cloud of the mirror universe. The quantum leap also refers to the precision with which these atoms can now be studied. In the past, the atoms were still wiggling too much due to residual heat, which blurred the measurements of their internal structure. It was like trying to take a high-resolution photograph of a person who is constantly shivering. No matter how good your camera is, the image will be fuzzy. By achieving this new level of deep, rapid cooling, the Alpha researchers have effectively told the antiatoms to stand perfectly still. This allows for spectroscopy measurements with a level of detail that was previously a theoretical dream. We can now peer into the heart of the antiatom and ask if it truly vibrates at the exact same frequency as regular hydrogen. If there is even a billionth of a percent difference, this new cooling technique is what will allow us to see it. Furthermore, this breakthrough solves the problem of trap depth. Because the magnetic fields used to confine neutral antihydrogen are inherently weak, the only way to make the trap deeper was to make the atoms colder. By reaching these record-breaking temperatures 8 times faster, the scientists have effectively made their magnetic bottle 8 times more secure. The atoms are now sitting so deep in the magnetic bathtub that they are virtually immune to the minor fluctuations in the environment that used to cause them to annihilate. This stability is what allows the 15,000 atom record to be possible. We have moved from a fleeting microsecond of existence to holding antimatter for hours, and eventually, perhaps, for days. The technical mastery required to achieve this cannot be overstated. The lasers used in the alpha experiment must be stabilized to a fraction of a hertz and synchronized with the pulsing of the antiproton decelerator. The timing must be perfect. If the laser pulse hits a nanosecond too late, the atom is gone. If the frequency is off by a hair, the laser adds heat instead of removing it, destroying the sample instantly. The 2026 achievement is a testament to the perfection of this synchronization. It represents a synergy between particle acceleration, cryogenic engineering, and quantum optics that has never been realized at this scale. This advancement also signals the end of the antiproton decelerator era as we knew it, and the beginning of the antimatter factory era. When you can cool particles this quickly, you can start thinking about throughput. You can start thinking about transporting these atoms to other areas of the CERN complex, or even to other laboratories. The 2026 record is the proof of concept for the portable antimatter traps that have long been a staple of science fiction. If you can cool them fast enough and hold them securely enough, the dream of moving antimatter out of the basement of CERN and into the wider world of experimental physics becomes a tangible reality. Ultimately, Alpha's quantum leap is about control. For the first time, we are not just victims of the volatile nature of antimatter, we are its masters. We have found the brakes for the most dangerous substance in existence, and we have found that those brakes are 8 times more powerful than we imagined. This record doesn't just represent a new number on a chart. It represents a threshold of maturity for the entire field of particle physics. We have moved from the era of discovery to the era of manipulation. By conquering the heat of the anti-atom, we have cleared the final technical hurdle to exploring the dark side of the universe. The bottle is finally cold enough. The trap is finally deep enough, and the lightning is finally standing still. This is the foundation upon which the future of energy, propulsion, and our understanding of the Big Bang will be built. The 2026 breakthrough has turned the impossible into the inevitable. With the cooling breakthrough of 2026, the alpha experiment has officially transitioned from a scientific longshot into the most precise laboratory in the world. As we look toward the rest of this decade, the ability to chill antihydrogen 8 times faster will be the standard by which all other hidden sector experiments are measured. It is the key that has finally turned in the lock of the mirror universe, and as the door swings open, we are finding that the ghosts we have been hunting are finally ready to be caught. Would you like me to continue with part 6? Or shall we adjust the focus of the next segments? When we speak of the recent triumphs at CERN, the number 15,000 rings out with the resonance of a grand achievement. For the scientists working within the ALPA collaboration, reaching a sustained trap of 15,000 antihydrogen atoms feels like ascending the summit of a mountain they have been climbing for decades. It is a staggering leap from the early days of the experiment, when the team celebrated the capture of a single, solitary anti-atom. To move from the singular to the thousands represents a change in the very nature of the work. We have transitioned from the era of detection, where the goal was simply to prove that an anti-atom could exist for a few milliseconds, to the era of accumulation. But as we marvel at this new scale, we must also ground ourselves in a cold, physical reality check. The word 15,000 sounds massive, even intimidating, especially when associated with a substance as volatile as antimatter. However, When we place that number on the scales of the macro world, we begin to understand just how far we have come and how impossibly far we still have to go. To the human mind, 15,000 of anything feels like a crowd. If you had 15,000 people in a stadium, the roar would be deafening. If you had 15,000 diamonds, you would be among the wealthiest individuals on Earth. But in the world of atomic physics, 15,000 is a ghost of a whisper. To understand the scale, we have to compare it to a gram, the standard unit of measure for a small amount of matter, like a single paperclip. A single gram of hydrogen contains roughly 600 sextillion atoms. That is a 6, followed by 23 zeros. In that context, 15,000 is not even a drop in the bucket. It is a single molecule in a vast global ocean. If you were to take all 15,000 antihydrogen atoms currently held in the alpha trap and annihilate them all at once, the result would not be a city-leveling explosion. In fact, it wouldn't even be enough energy to boil a single thimble of water. It would be a flash of light so faint, it would be nearly impossible to see with the naked eye. This is the central paradox of antimatter research. We are celebrating a record-breaking quantity that is still, for all intents and purposes, almost nothing. If you were to collect antimatter at the current record-breaking rate of the alpha experiment, it would take longer than the current age of the universe to accumulate a single gram. This reality check is essential to debunking the immediate fears of antimatter bombs or unlimited energy batteries being rolled out next year. We are not yet in the business of mass production. We are still in the business of artisanal, atom-by-atom craftsmanship. The 2026 record is a monumental achievement in the history of precision engineering, but it is not yet a threat to the global energy market or a weapon of mass destruction. So, if 15,000 atoms can't power a light bulb or level a building, why does this number matter so much? Why is the scientific community treating this like a revolution? The answer lies in the shift from observation to experimentation. When you have only 1 or 2 atoms, you are a passive observer. You watch the atom flicker into existence, and you hope you can see it before it dies. You are limited by the statistical noise of a single event. But when you have 15,000 atoms held stable in a magnetic trap, you have a sample, you have a cloud, you have enough material to actually perform physics. This scale allows for the first high-precision measurements of the mirror universe. With 15,000 atoms, scientists can hit the sample with a laser and measure the response with incredible accuracy. Because they have a large number of atoms, they can repeat the measurement thousands of times within the same trap, averaging out the errors and looking for the tiny, subtle discrepancies that might exist between matter and antimatter. It is the difference between trying to hear a song through a wall with one ear and being in the front row of the concert with a professional microphone. 15,000 atoms provide the volume necessary to hear the music of the spheres. Furthermore, this scale allows for the first real tests of gravity. In a project known as AlphaG, the team is now able to release their cloud of 15,000 atoms and watch how they fall. With one atom, you can't be sure if it fell because of gravity or because it was bumped by a stray magnetic fluctuation. But with 15,000, you can watch the entire cloud move as a single unit. You can measure the statistical distribution of their descent. This is the first time in human history we have had enough antimatter in one place to ask a fundamental question. Does the evil twin of matter fall down, or does it fall up? Without the scale of 15,000 atoms, that question would remain purely theoretical. Now, it is an empirical measurement. This achievement also signals a breakthrough in containment stability. Storing 15,000 atoms isn't just about catching them, it's about keeping them. The more atoms you pack into a magnetic trap, the more they interact with each other. They can collide, exchange energy, and knock each other out of the magnetic bathtub. Reaching the 15,000 mark proves that our magnetic bottles are now sophisticated enough to manage a multi-body system. We have moved past the stage of holding a single marble in a bowl to holding a handful of water. This is the foundation of future high-density storage. If we can master the stability of 15,000, we can begin to design the traps that will hold 15 million and eventually 15 billion. There is also a profound symbolic weight to this number. For decades, the primary argument against the feasibility of antimatter technology was that we could never make enough of it to matter. Critics would point to the LHC, or the antiproton decelerator, and say that the output was so pitifully small that it would never be more than a hobby for theoretical physicists. The leap to 15,000 atoms, supported by the 8-fold increase in cooling speed, is a direct rebuttal to that skepticism. It shows a clear, accelerating trajectory. We are seeing an antimatter Moore's law beginning to take shape. The scale of the doom associated with these atoms is not in their current explosive potential, but in the message they send to the future. The barrier to mass is falling. We must also consider what this scale does for the standard of proof in science. In particle physics, you need 5 sigma certainty to claim a discovery. That requires a massive amount of data. When your sample size is 1, you can't prove anything. When your sample size is 15,000, you are entering the realm where you can claim a discovery with total confidence. We are now at the point where we can definitively compare the God element to the ordinary hydrogen that makes up our stars and our water. We are no longer guessing. We are measuring the fundamental constants of the mirror world with a ruler that is 15,000 units long. Ultimately, the 15,000 atoms currently held at CERN represent a bridge. On one side of the bridge is the world of pure theory, where antimatter was a ghost that vanished the moment you looked at it. On the other side is a world where antimatter is a material, a substance that can be weighed, measured, cooled, and transported. We are walking across that bridge right now. The scale of 15,000 atoms is the critical mass for science. It is the point where we stop asking if antimatter exists and start asking what we can do with it. It is the end of the beginning. While it may not be the doom that pop culture imagines, it is the most significant collection of matter's shadow ever assembled in one place. It is a tiny, glowing cloud of the impossible, held in a magnetic cage, waiting for us to ask the right questions. And for the first time, we have enough of it to hear the answers. To discuss the future of antimatter, one must eventually move past the wonder of quantum mechanics and confront the cold, hard mathematics of the ledger. In the realm of economics, antimatter is not just an exotic state of matter, it is the ultimate luxury item, a substance so rare and difficult to produce that it makes gold, diamonds, and even weapons-grade plutonium look like common street gravel. While the scientific community celebrates the capture of 15,000 atoms, the financial world looks at the price tag and shudders. Estimates for the cost of antimatter vary, but the most widely accepted figure is a staggering $62.5 trillion per single gram. To put that in perspective, The entire annual gross domestic product of the planet Earth is roughly $100 trillion. A single gram of this material, roughly the weight of a paperclip, is worth more than half of everything produced, sold, and traded by the human race in a year. This economic reality is the single greatest barrier standing between us and the sci-fi future of warp drives and infinite energy. The reason for this astronomical price tag lies in the sheer brute force inefficiency of our current production methods. We do not find antimatter. We have to manufacture it from scratch. And the process is akin to trying to assemble a luxury watch by throwing a bag of gears at a wall and hoping they fall into place. At CERN, antiprotons are created by firing a high-energy beam of protons into a metal target, usually made of iridium or tungsten. These collisions are incredibly violent, creating a chaotic spray of subatomic debris. Amidst billions of collisions, only a tiny handful of antiprotons are produced. It is a process of extreme attrition. For every million protons we fire, we might successfully harvest only 1 or 2 antiprotons. This leads us to the efficiency paradox. In popular culture, antimatter is often depicted as the ultimate fuel source. But in the present day, it is actually the most inefficient energy storage device ever conceived. To create that single gram of antimatter, we would need to run the Large Hadron Collider and its supporting infrastructure for millions of years. The electricity bill alone would bankrupt every nation on Earth. Currently, it takes about 1 billion times more energy to create an antiproton than that antiproton will ever release when it annihilates. We are essentially spending a mountain of coal to create a single spark. From a purely economic standpoint, this makes antimatter a terrible investment for energy production. It is a battery that loses 99.9999999% of its charge the moment you try to fill it. Furthermore, the infrastructure required to support this production is some of the most complex and expensive machinery ever built. The antiproton decelerator at CERN is a massive high-tech factory that requires a small army of world-class physicists, engineers, and technicians to operate. The maintenance costs, the cryogenic cooling systems, and the vacuum pumps that must run 24/7 add layers of overhead that ensure the price remains in the trillions. We are not just paying for the atoms, we are paying for the 2 7-kilometer ring of superconducting magnets and the decades of research that made them possible. Until we find a way to skip the collision phase and manufacture antimatter directly, it will remain the most expensive substance in the history of the species. This economic bottleneck often leads to a common question. If it is so hard to make on Earth, why don't we just go out and get it? The universe is vast, and surely there must be clouds of antimatter floating in the void, waiting to be harvested. This is where we must debunk the scooping from space myth. While it is true that cosmic rays and high-energy events in space create small amounts of antimatter, there are no anti-planets or anti-moons in our local neighborhood. If there were, the boundary where the solar wind meets the antimatter body would be a source of constant blinding gamma radiation. The sky would be glowing with the light of perpetual annihilation. Since the universe is remarkably quiet in the gamma-ray spectrum, we can conclude that antimatter is just as rare in space as it is on Earth. There have been proposals to mine the Van Allen radiation belts around Earth, which are known to trap a tiny number of positrons and antiprotons produced by cosmic ray collisions with our atmosphere. In theory, a satellite with a massive magnetic scoop could orbit the Earth and gather these particles over time. However, The density of these particles is so low that the cost of building, launching, and maintaining such a satellite would far exceed the value of the antimatter collected. You would be spending billions of dollars to harvest a few picograms of material. It would be like trying to pay off a mortgage by picking up pennies in a desert. The fuel for your car to get to the desert would cost more than the pennies you find. The economic reality of 2026 is that we are still in the pre-industrial phase of antimatter. We are like the early alchemists who could create a tiny flake of gold from lead, but spent a fortune in mercury and coal to do it. The breakthrough at alpha, while scientifically massive, doesn't immediately change the price of the material. What it does, however, is move the needle on the utility side of the equation. By trapping 15,000 atoms and cooling them 8 times faster, we are making our investment in that energy more durable. If we can hold the atoms longer and study them more effectively, the value of each atom increases. We are getting more science per dollar. To move toward an antimatter economy, we would need a fundamental shift in how we view energy. Currently, we view antimatter as a fuel to be burned. In the future, it might be viewed as a medium for transport. If we ever develop the technology to produce it at scale, the cost would likely drop, but it would still never be cheap. It will always be the high-octane fuel for the elite for deep space missions, where every kilogram of weight matters. In space travel, the economics shift. If it costs $10,000 to launch a liter of water into orbit, then a fuel that is 1 billion times more dense than chemical rockets starts to look like a bargain, even if the production cost is high. Ultimately, the $62.5 trillion price tag is a reflection of our current limitations. It is a measurement of our struggle to master the most fundamental symmetry of the universe. We are currently paying the ignorance tax, the high price of doing something we don't fully understand yet. As experiments like Alpha continue to break records, and as our understanding of the mirror universe matures, the efficiency will inevitably climb. But for now, we must accept that we are playing with the most expensive toys in existence. Every time the beam fires at CERN, we are burning through a fortune to catch a ghost. It is a testament to human curiosity that we are willing to pay such a price. But it is also a reminder that the key to infinite energy is currently locked behind a vault that costs the world to open. To answer the question that serves as the heart of this entire exploration, whether CERN has finally found the key to infinite energy, we must reconcile a staggering mathematical truth with a sobering physical reality. In the realm of theoretical physics, the promise of antimatter is nothing short of divine. It represents the absolute ceiling of energy density allowed by the laws of nature. If we look strictly at the numbers, antimatter is the ultimate holy grail, because the reaction between matter and its mirror twin is 100% efficient. The amount of power locked within a tiny amount of substance is difficult for the human mind to grasp. A single gram of antimatter, through total annihilation, would release approximately 90 trillion joules of energy. To put that into a more relatable context, 1 gram of antimatter reacting with 1 gram of matter would produce an explosion equivalent to roughly 43 kilotons of TNT. That is nearly 3 times the destructive power of the atomic bomb dropped on Hiroshima. From a civilian perspective, that same single gram could theoretically provide enough electricity to power a major metropolis like New York or London for an entire day. It is the most concentrated form of energy storage possible in the known universe, a literal condensed version of the power of the stars. However, the leap from this theoretical potential to the concept of infinite energy for the masses is currently blocked by a fundamental misunderstanding of what antimatter actually is in our current technological context. In the popular imagination, we often think of antimatter as a primary fuel source, something we can discover, mine, or harvest, like oil, coal, or uranium. We imagine finding antimatter deposits in deep space that will solve our energy crisis forever. But the reality is far more restrictive. Because our universe is made almost entirely of regular matter, there is no naturally occurring antimatter for us to simply go out and collect. Instead, every single anti-atom we wish to use must be manufactured by us, one by one, in particle accelerators. This leads us to the most important reality check in modern physics. Antimatter is not a fuel source, it is a battery. This distinction is crucial to understanding why we haven't solved the world's energy problems yet, despite the record-breaking 2026 alpha results. To create antimatter, we have to pump an incredible amount of energy into a system using electricity from the national grids of France and Switzerland to accelerate protons to near-light speeds and smashing them into targets. The laws of thermodynamics are notoriously unforgiving here. According to the law of conservation of energy, you can never get more energy out of a system than you put into it. In fact, due to the extreme inefficiencies of our current production methods, we are putting in billions of times more energy than we could ever hope to get back. We are essentially spending the energy output of a major power plant to create the energy equivalent of a single matchstick. Unless we find a way to harvest antimatter from the vacuum of space, or find a naturally occurring source from the early universe, it will always be a net loss energy medium. It is an incredible way to store energy in an incredibly dense form, but it is not a way to generate new energy for a hungry planet. This realization often brings a sense of disappointment to those raised on the dreams of Star Trek and the optimistic futurism of the late 20th century. In the Star Trek universe, the USS Enterprise is powered by a matter-antimatter reaction assembly or a warp core. This fictional technology uses antimatter as the primary energy source to create a warp bubble, allowing the ship to travel faster than light. In that narrative, antimatter is the gasoline in the tank that keeps the Federation running. But even in sci-fi, the writers often glossed over the how to make it part. The difference is that in fiction, the efficiency of creation and the stability of storage are assumed to be solved problems. In our real-world year of 2026, we are still at the very beginning of that journey. We have proven we can make the gas, and we have proven we can build a tank that holds 15,000 atoms, but we are still paying a fortune for every drop. If antimatter takes more energy to make than it provides, we have to ask why CERN is pushing so hard to break these records. If it isn't the key to infinite energy for Earth's power grid, what is its actual value? The answer lies in the specific utility of energy density. While antimatter might be a terrible way to power a toaster in your kitchen or a heater in your home, it is the only way to envision true interstellar travel. Current chemical rockets are heavy because they have to carry tons of fuel just to lift a tiny payload. Most of a rocket's weight is just the fuel needed to move the rest of the fuel. It is an equation of diminishing returns. Because antimatter is so dense, a few milligrams could replace thousands of tons of chemical propellant. For a mission to Mars, or eventually to another star system, the inefficiency of making the antimatter on Earth becomes a side note. What matters is how much energy you can pack into the smallest possible mass once you leave the Earth's atmosphere. In this context, the high cost of the battery is worth the performance it provides in the vacuum of space. We aren't looking for a replacement for solar or wind power on Earth. We are looking for the interstellar spark that will take us to the stars. The energy released per kilogram of antimatter is orders of magnitude beyond anything else in our arsenal. It is not just better than nuclear power, it is a different league of existence. Nuclear fission converts only about 0.1% of mass into energy, and fusion converts about 0.7%. Antimatter sits at a perfect 100%. This is why physicists are so obsessed with these 15,000 atoms. We are currently at what could be called the transistor stage of antimatter. In 1947, the first transistor was a bulky, hand-built device that could barely amplify a signal. Today, your smartphone has billions of them. The Alpha Experiment's 2026 record is that first transistor. It proves the mechanism works, it proves we can hold the charge, and it proves we can cool the volatility of the mirror universe. It is the proof of concept for a new kind of civilization. So, to answer the title's provocation, has CERN found the key to infinite energy? Not in the sense of a free lunch, but they have found the key to a new type of energy economy. They have found the way to store the most powerful force in nature inside a magnetic cage. The 2026 breakthrough is the moment we officially moved antimatter from the realm of magic into the realm of applied engineering. We have stopped dreaming about the warp drives of the 24th century and started building the storage tanks for the 21st. We are learning how to handle the God element, not as a mythical force, but as a manageable, storable resource. The key doesn't open a door to a room full of free power. It opens a door to a future where energy is so concentrated that the entire solar system becomes accessible to us. We have tamed the wildest substance in nature, and while we are still far from fueling a starship, we have finally proven that we can hold the fire of creation in our hands without being consumed by it. The era of the antimatter fantasy is over. The era of the antimatter battery has begun. Among the many legends of science, few are as iconic as the image of Isaac Newton sitting beneath an apple tree, watching a piece of fruit tumble to the ground and realizing that the same force pulling that apple governs the motion of the moon. It is the birth of our understanding of gravity, a universal, inescapable pull that affects everything made of matter. But for nearly a century, a silent, nagging question has occupied the back of every physicist's mind. What would happen if that apple were made of antimatter? If Newton had been sitting under a tree in a mirror universe, would the anti-apple still hit him on the head, or would it defy every intuition we have and fall upward, drifting away into the clouds? This is not just a whimsical thought experiment or a plot point for a science fiction novel. It is a fundamental test of the very fabric of space and time. To answer it, the researchers at CERN developed the Alpha-G experiment, and the results from this vertical quest have finally provided a definitive look at the weight of the mirror world. The motivation for this experiment lies in the bedrock of modern physics. Albert Einstein's general relativity. Einstein proposed that gravity is not a traditional force like electromagnetism, but rather a curvature of space-time itself. Imagine placing a heavy bowling ball on a trampoline. the fabric stretches and curves. Anything else you place on that trampoline, whether it's a marble, a feather, or a grain of sand, will roll toward the bowling ball because of the shape of the fabric. In Einstein's view, space-time is the trampoline. According to his weak equivalence principle, the way an object falls should depend only on its position and its initial velocity, not on what it is made of. Space-time should not care if you are a proton or an antiproton, a human being or a ghost. If you have mass, you must follow the curve. However, until very recently, this was a massive, unproven assumption when it came to the dark side of the particle zoo. The doubt persisted because antimatter is so fundamentally opposite in every other category. It has the opposite charge, the opposite magnetic moment, and the opposite internal quantum numbers. Some theorists argued that perhaps this opposition extended to gravity. If antimatter possessed what we might call negative gravitational mass, it would be repelled by the Earth. This anti-gravity would have been a revolutionary discovery, offering an immediate and elegant solution to the mystery of why the universe didn't annihilate itself after the Big Bang. If matter and antimatter repelled each other, they would have naturally drifted into separate regions of space, preventing the great cosmic suicide and explaining why we don't see antimatter galaxies today. But science does not thrive on elegant stories. It thrives on empirical data. To get that data, the ALPA team had to build what is essentially the world's most sophisticated drop tower. This is the ALPA-G apparatus, a towering, vertical vacuum chamber that stands in stark contrast to the horizontal accelerators usually seen at CERN. The engineering challenge of this experiment is almost beyond comprehension. Gravity is an incredibly weak force at the atomic scale. To a single atom of antihydrogen, the electrical and magnetic forces from the surrounding equipment are billions of times stronger than the pull of the entire Earth. Trying to measure the effect of gravity on an antiatom is like trying to hear the sound of a single pin dropping in the middle of a heavy metal concert. If there is even a tiny, microscopic stray magnetic field, perhaps from a piece of unshielded wire or a passing vehicle outside, it will yank the antiatom around with a force that completely masks the tug of gravity. The experiment begins by trapping a cloud of these elusive antihydrogen atoms using the same magnetic bathtub technology we have explored. But instead of just holding them, ALPA-G must release them. The scientists carefully balance the magnetic fields at the top and bottom of the vertical chamber, creating a perfectly level magnetic floor and ceiling. Once the atoms are cooled to within a fraction of a degree of absolute zero, minimizing their random thermal wiggling, the magnetic barriers are slowly lowered. The researchers then wait and watch with high-precision detectors to see where the atoms go. Do they leak out through the top, or do they tumble out through the bottom? This is a game of statistics played with the ghosts of the universe. In late 2025 and throughout 2026, the results of this vertical release were meticulously analyzed. The question was simple: would the mirror stay true to Einstein, or would it break the rules? The data revealed a clear and unmistakable pattern. When the magnetic gates were opened, the antihydrogen atoms did not drift upward. They did not float toward the ceiling of the laboratory. Instead, they fell. They tumbled toward the bottom of the apparatus, obeying the same 9.8 meters per second squared acceleration that governs every falling object on our planet. For the first time, humanity has witnessed antimatter falling down. The significance of this result is twofold. First, it is a staggering confirmation of general relativity. Einstein's theory has survived yet another attempt to break it, proving that even the most exotic and volatile substance we can create is still subject to the fundamental geometry of space-time. It tells us that gravity is indeed a universal property, a common language spoken by both matter and its mirror twin. The weak equivalence principle holds firm. Space-time is the same trampoline for everyone, regardless of their electrical charge. However, for many in the scientific community, the result is also a bit of a beautiful disappointment. If antimatter had fallen up, we would have had a new physics explosion. It would have upended our understanding of the universe and provided a magic bullet answer to the matter-antimatter asymmetry problem. By falling down, antimatter has essentially told us that the mystery of our existence remains unsolved. We still don't know why matter won the war at the beginning of time, because we can no longer blame it on a gravitational repulsion that kept the two sides apart. The mirror is more perfect than we hoped, which makes the tiny flaw that allowed us to exist even harder to find. But we must not overlook the triumph of the measurement itself. To hold 15,000 anti-atoms still enough, and shield them well enough to see the tiny, gentle tug of the Earth's gravity is a pinnacle of human engineering. It is the ultimate gravity test. It proves that we have reached a level of mastery over the hidden sector where we can begin to treat these particles not just as fleeting anomalies, but as test subjects for the most fundamental laws of nature. We are no longer just asking, what is it? But how does it behave in our world? This result also closes the door on most anti-gravity propulsion theories that relied on the idea of antimatter being naturally repelled by planets. If we ever build a warp drive or an antimatter-powered ship, we won't be falling away from Earth. We will be using the sheer energy of annihilation to push against the curve of space-time. The gravity test has anchored our sci-fi dreams in real-world physics. It tells us that while antimatter is the ultimate fuel, it still has to play by the rules of the house. As the Alpha-G experiment continues to refine its measurements, looking for even smaller deviations, perhaps a fraction of a % difference in the rate of fall, we are entering a new phase of precision cosmology. We are checking the fine print of Einstein's work. We have confirmed that the anti-apple falls down, but does it fall at exactly the same speed? Is there a hidden fifth force that acts slightly differently on the mirror sector? These are the questions that will occupy the next decade of research. For now, we can say with certainty that the mirror world is not a place of inverted gravity. It is a place where the same invisible hands that guide the planets also guide the ghosts. We have looked into the dark and found that it follows the same path as the light. General relativity remains the undisputed king of the cosmos, and the mirror world, for all its strange beauty and destructive power, is still part of the same curved universe that we call home. We have seen the anti-apple fall, and in its descent, we have found a deeper connection to the symmetry of our origins. The journey into the mirror universe, which began as a series of flickering shadows and fleeting detections, has reached a definitive turning point as we move through 2026. We must be honest about where we stand. We have not solved the global energy crisis. We are not yet plugging our cities into antimatter reactors, nor are we fueling starships for a weekend trip to Proxima Centauri. The massive power plants of our world will continue to run on wind, sun, and traditional nuclear fission for the foreseeable future. However, what has happened within the concrete walls of CERN's Alpha experiment is something perhaps even more profound than a new power source. We have tamed the wildest, most volatile substance in the known universe. We have taken the God element, a substance that was once a purely mathematical ghost, and turned it into a manageable laboratory material. We have transitioned from the era of accidental discovery to the era of absolute mastery. For decades, antimatter was the ultimate forbidden fruit of physics. It was the substance that nature seemed determined to keep away from us, vanishing the instant it touched our reality. To study it was to chase a ghost through a dark room with a strobe light. But the recent record of 15,000 atoms, held stable and cooled 8 times faster than ever before, represents the construction of a permanent sanctuary for that ghost. We have built a hearth for the most dangerous fire in existence. This is the same evolutionary leap that early humans took when they moved from fearing the lightning-strike forest fires to carrying a glowing ember in a hollowed-out horn. We have captured the spark of the Big Bang, and we are finally learning how to keep it from going out. As we look toward the next decade, the roadmap for this technology is shifting from static observation to dynamic transport. One of the most ambitious projects currently emerging from this breakthrough is the concept of the portable antimatter trap. Historically, if you wanted to study antimatter, you had to go to Geneva. You had to bring your entire laboratory to the antiproton decelerator. But with the new levels of stability and cooling efficiency we have achieved, we are entering the era of antimatter on the move. Scientists are already designing traps that can be loaded onto specialized vehicles, moving the mirror universe across the CERN complex, or even across borders to other research facilities. This is the industrialization of the impossible. Once we can move antimatter as easily as we move liquid nitrogen, the pace of discovery will accelerate exponentially. We will be able to use these anti-atoms as high-precision probes in material science, medicine, and deep space communications. The next 10 years will likely see the first high-density storage prototypes. While 15,000 atoms is a monumental achievement, the next goal is the billion-atom threshold. At that scale, we stop talking about individual particles and start talking about bulk antimatter. This is where the physics gets truly exotic. We may see the creation of anti-molecules or even anti-crystals. We will be able to observe how these substances interact with each other without the constant interference of regular matter. This isn't just about energy. It's about expanding the periodic table into a second, mirrored dimension. We are building the foundation for a new chemistry, an anti-chemistry that follows the same rules but uses a completely different set of building blocks. In the realm of space exploration, the breakthrough in cooling and storage is the first real heartbeat of the interstellar age. We have long known that chemical rockets are too weak and nuclear thermal rockets are too heavy to take humans beyond our solar system. Antimatter is the only fuel with the energy density required to bridge the gap between the stars. By proving that we can cool antihydrogen 8 times faster and hold it in a magnetic cage that obeys the laws of gravity, we have cleared the most significant technical hurdle for future propulsion systems. We are no longer asking if we can store the fuel, we are now asking how large we can build the tank. The children born today may grow up in a world where the first antimatter-catalyzed rockets are undergoing testing, turning the deep space void into a navigable highway. This mastery also brings us closer to solving the existential question of our origins. By holding the mirror universe still enough to examine its every detail, we are looking for the tiny flaw, the microscopic asymmetry that allowed us to exist. We are no longer just observing the universe's most volatile secret, we are interrogating it. Every second that those 15,000 atoms remain suspended in their magnetic cradle is a second where we are winning the war against annihilation. We are forcing the universe to reveal the crack in its perfect symmetry. It is easy to get lost in the numbers, the trillions of dollars, the thousands of atoms, the millions of degrees. But the true significance of the 2026 Alpha record is human. It is a testament to our refusal to be sidelined by the vast, cold indifference of the cosmos. We live in a universe made of matter, and for a long time, we were content to assume that was the only story. But our curiosity drove us to look for the other half. It drove us to build machines that can recreate the first moments of time and traps that can hold the most destructive substance ever conceived. We have taken the universal solvent, the substance that should destroy everything it touches, and we have made it sit still. We have mastered the God element not by overpowering it with energy, but by understanding it with precision. As we close this investigation into the dark side of the laboratory, we must realize that the wall between our reality and the hidden sector has never been thinner. The key to infinite energy might still be a few generations away, but the door is finally unlocked. We are no longer guests in a universe we don't understand. We are becoming the architects of a reality that includes both the light and the dark. The mirror has been caught, the ghost has been caged, and the future is glowing with the light of 1,000 annihilations. The era of wondering what if is over. We are now in the era of what's next. Whether we use this power to reach the stars or to finally understand the very first second of our existence, the record at CERN has ensured that we are the masters of the most powerful force in nature. We have found the key. Now, we just have to decide which doors we are brave enough to open. Good night, and see you in the next video.